Today we have Dan Andrews, who is trying to find water on the moon. He's the project manager of the Resource Prospector program at NASA Ames. Without further ado, here's Dan.
It's great to be here. I've been looking forward to this talk for some time. Little quick note, I was just at a conference in the UK and there was a whole bunch of discussions about data analytics associated with CubeSat missions and just in general. And one of the companies that was there was talking about the ability to judge how an economy is doing based on the relative fill of a parking lot in an area, or parking lots. You guys are doing just fine here. It's tough to find parking. All right, so I'm here, as Mary had indicated, to tell you about the Resource Prospector mission. It's a follow-on mission to LCROSS, which is a mission that did indeed definitively note that there's water on the polar regions of the moon, and I'll tell you a little bit about that. A little bit about the whole ISRU, in-situ resource utilization topic. And then I'd like to focus probably about half the presentation on our status as a mission and some of the cool development work that we're doing. So first of all, with respect to lunar volatiles, this has been a topic that has existed for a few decades, but I'm featuring some of the notable missions that really helped us steer where we are today. The Clementine mission, which was not a mission trying to look for volatiles on the moon, it actually had other multiple purposes, but bistatic radar testing of the polar regions of the moon indicated that, wow, there's some real high hydrogen concentrations in these polar regions. And it was, I think, where some of the first thought went into, could that actually be water? No, that can't be water. It's bone dry up there. There's no way that could be water. Lunar Prospector, which came around about 4 years later, actually confirmed and measured the hydrogen levels. But again, the question persisted. Is it elemental hydrogen? Is it hydrogen bound in the soil? Or is it hydrogen bound in water? You couldn't quite tell. So what was needed was a mission like LCROSS, and we were co-manifested with the Lunar Reconnaissance Orbiter mission that actually went in, landed with vigor, as we like to say, with an impactor that went into a polar region crater, kicked up the soil that was there, whatever's there was kicking it up into the sunlight. We had a shepherding spacecraft follow in behind it and measure what was in the soil. And we were able to confirm quite a bit of water ice. Now on Earth scale, it's not quite a bit of water ice. It's maybe of the scale of the Mojave Desert, a lot of water. However, on a scale of both poles, all the craters and all this, truly trillions and trillions of gallons of water potentially there. So great, we answered the big question, but so what? The next step is to actually understand it on more human scales, and that's where Resource Prospector comes in. On the scale of maybe meters as opposed to kilometers, what's the nature of the soil, of the volatiles in the soil? Is it ice in blocky form? Is it instead fine like sand in there? Is it higher concentrations here but lower concentrations there? What about the role the sun plays? So a mission to go in there and actually understand the nature of the volatiles is essential and the obvious next step. So on the EVOLVABLE Mars campaign, and you can see a Resource Prospector right here. The idea is that the big goal is Mars. The big goal is to get boots on the ground in Mars. However, that's a very tough task, and there's much that we could learn along the way and using the moon to our advantage. Moon to our advantage can mean on a human scale, what it's like to live and operate in a certain environment, although the moon looks very different than Mars. But it also can mean from a resource point of view, which is really where my interest lies and where Resource Prospector comes in. So I'm going to show you a mission animation. Our original design is to go on, say, an EELV, say a Falcon 9 styled rocket. This is us taking off from the Cape as an illustration. Fairing pops off. We're now on our way to the moon. That's why you could see the lander and the rover there. We've separated from the rocket. We have a solid rocket motor on the bottom of the lander, which is firing right here, just finished. And the whole point of that was to be captured by the moon, right? To not fly right by it. So we use that to head on our critical descent trajectory. I think at this point you're going to see the solid rocket motor kick off. We're done with that. And now we start to reorient ourselves for the descent. One thing of note here, this looks probably like no other lander that you've seen before. And that's one of the key thrusts of this mission that I'll get into in a little bit. And that is we're trying to be very simple, very risk tolerant, and very cost effective. That's what LCROSS was. LCROSS rewrote the books on the moon for $79 million, which on a NASA scale is incredibly cheap for how important that mission was. We're trying to extend some of that to a much bigger mission like Resource Prospector. So we go in, we trim out our descent, we get down to a slow fall rate, and you can see here, rover's ready to go. The lander actually has 2 different ways that you can egress, because we don't know that we might land partially on a rock in some sort of obstacle way, so we want to be able to double our chances to get off. Now this is the Resource Prospector surface segment, we call it. That means it's the rover and the payload system together. Because it can move in all directions, it can crab walk, we immediately get on the sun to be power positive. And then we can move in any direction, of course, at that point. One of the big benefits of having the steering system that we have in this arrangement. What you're looking at here is an illustration of the neutron spectrometer system actually able to look down, say, a meter through the soil without digging and actually look for indications of hydrogen, which would tell us where we might want to drop the drill and actually ground truth that. What that means is we're actually going into a permanently shadowed region, and by definition, permanently shadowed, it in its 2 or 3 or 4 billion year existence has never seen the sun. So the way you picture that is, say, if my head was the sun and this is the moon, as the moon's moving around the Earth and around the sun light is all tangential to the polar regions. So it actually shoots right over the top of some of these craters that are on the polar regions that are very susceptible to be able to trap the water ice. So we got to go down into these areas that are actually maybe 50, 60, 70 degrees Kelvin, maybe colder than Pluto, and somehow have our machinery work. So there's quite a bit of challenging that we are doing of ourselves right now. So questions RP wishes to answer. Resource extraction needs to be economical. NASA won't get into the business of trying to provide resources, at least not in the long term. That's the job of the commercial industry to figure that out. But we need to answer some fundamental questions up front in order for the commercial world to be able to understand how tough or maybe easy this is going to be. So resource extraction must be economical. What are the distribution of those volatiles vertically and horizontally? What's the overburden story? Let's say you can't get to this water ice that we know is there, but you have to drill down 2 meters to get it, and it only exists in a permanently shadowed region, not in a semi-permanently shadowed region. That's a very different engineering problem than if it's littered on the surface, and you could just be scooping along the way and then putting it into a hopper and baking it out. These are questions we need to answer. Working environment. All the same logic here. Sun versus shadows, soil mechanics, trafficability. Is it easy to navigate over it? Would you have these mobile platforms that can go in there and actually scoop this up, or is it more static? So our job on RP is to take a look at 4 different areas. This is our goal. Illustrated in the top right, you could see with color coding different types of environments in a given area on one of the polar regions. And then the bottom right illustrates a zoom in of those. Dry areas. We really believe in the dry areas that are up in the sun. There's not going to be any water ice there, and there may not even be water ice in the soil because it would have, over all those billions of years, baked out from all the radiation and energy being dumped into the soil from the sun. But we're not sure of that. We just think that makes sense. So we want to go try that out. Surface and permanently shadowed regions, it may be literally on the surface. We already have seen indications of frost from other missions. Light weather conditions, if you will, even though this is an airless body. Shallow, ice that's stable in the first 50 centimeters versus 50 to 100 deeper. All these things are answers that we wish to be able to get on this mission. Our customer, which is NASA headquarters in Washington, D.C., has really given us a really interesting framework. Remember, I told you we're a different kind of mission. we're executing differently. They gave us 2 requirements, which I've synopsized here. Okay, they're pretty high level. The whole goal is that they didn't want to give us incredibly stringent requirements at level 1, as we call it, because if you have any residual risk, because you're trying to do things cost effectively, you could be a failure. So they want to guide with the level 1s and allow us to derive more detailed requirements from that and take chances, take a risk. And in doing so, we could be single strung, which is our term for no redundancy, right? Test the heck out of the system, go fly it, and maybe accomplish something great like LCROSS for much less money than would normally be required for a NASA mission. So multiple paths to mission success. I like to call RP a lightweight, risk-tolerant, cost-effective mission. I'm already finding that some of our early cost estimates are 1/3 or maybe even less the cost of a typical NASA mission. RP is not going to be a technical marvel. This one's really hard for the engineers, of which I am one, that it's not going to be this amazing achievement from a technical point of view. Where we're putting the amazing or the marvel part is in what it could answer. But how we go about doing it should be as proven as we can possibly get it. If we can get things off the shelf, if there's things that have been demonstrated on other missions, let's use them and then go do something great with that, including influencing NASA's methodology going forward, which is a personal goal of mine. We are, of course, going to go after the minimum success first, then we go for the full success, and then we have fun. That could take a lot of different forms. When we answer some of those fundamental questions within 1 lunar day, do we, when lunar night comes, which may be, depending on your location, 6 to 14 days later, Earth days later, it'll get very, very cold. We're not required nor designed to make it through the night. So do we just find a place that has the shortest night and then go sleep finally, and then come back in a Earth week, say, and see if it comes back to life and we can continue the mission? Do we just drive as far as we can into a permanently shadowed region until we can't communicate with it anymore? Lots of different possibilities. So let me talk just very quickly about how the neutron spectrometry works in a very simple way. I'm an engineer, not a lunar scientist, so this is how I look at the opportunity here. So galactic cosmic rays are continuously hitting the visible regions of the moon. And in doing so, they shatter nuclei, and you get all this flux that comes flying out of the soil. That neutron spectrometer that's sitting on the front that you saw very simply animated with the blue pathways and so forth in the video are what we're able to measure. And if we find an area that's especially interesting, you can see the neutron count rate there, we could actually use our drill down to as much as 1 meter deep in the soil, pull the material up, and in the video you would see that we actually cook the material. We have a cleverly named device called an oven. That's actually an acronym, but it's also an oven. That cooks the soil, a crucible that we deliver into the oven, cooks it and measures all the constituents that come baking off. And so that's the whole key, the whole trick behind the mission. So we set ourselves in a very ambitious goal in fiscal year 15. That is, can we actually, from our requirements in a single year, go from requirements to a preliminary design while going through all the gate reviews that NASA has, but an expedited version of them, manufacture the hardware, build the hardware, conduct testing on it, and actually fly the mission, air quotes, fly the mission on Earth, all in a year. And so this was the rover that we had designed, and I'll give away the answer. We did it in 10 to 11 months. It was very impressive. And so I'm going to walk you through now some of the work that we've done. Some of this predated the 1 year. This is a little bit before, but I want to use it to illustrate some of the work that we've done. So what you're seeing here is the KREX rover at NASA Ames Research Center out in the Roverscape. And we've got the neutron spectrometer right up here in the front. That's the one that you saw in the video. And then a gamma ray source out in the front on this proboscis that sits out front, because one of the many beauties of Earth is that we have our atmosphere to protect us from some of the radiation that we won't be protected from on the moon. And so that's a radiation source, low-level radiation source that is pummeling the soil in front of the rover, and the neutron spectrometer can then take measurements as if it would out in the native lunar environment. We also have an instrument called NIRVSS, which is a near-infrared spectrometer system. So you got a neutron spectrometer, a near-infrared spectrometer. This one does not have the ability to look down in the soil. That's what the NSS is for. This one has the ability to look at the surface, like right on the surface. And so what's very good about that is it allows us, as we're cruising and doing our mapping, to see what's on the surface, but also if we bring materials up to the surface, we could look at what's coming up and actually get a vertical distribution of what we're finding down at that drill point. We've then set up tests in thermal vacuum chambers. This is a SOSO image of a container, say about 1 foot in diameter, maybe about 3 feet tall, that has been doped with soil, lunar simulant, and a certain amount of water as a function of depth. We put it in a thermal vacuum chamber, take our drill system, actually drill through it and see if we can recreate what we know is the shape of the volatile distribution in that canister. And this is a plot of what we had found in our data, and it did indeed match very well to what was going on in there, and that was at, as near as we could reasonably get, lunar temperature in a permanent shadow region and at vacuum. So that was a very good test. You can see here the crucible that we're filling, and this is the drill system bringing up materials and dumping it on the surface, and that's where the near-infrared spectrometer can take a look at it. Now we're evolving the design a little bit further. Here's the oven that I was referring to. You can see it's red hot in here. It's just truly a ceramic double wound oven heating system and a scissor lift that pushes the crucible up into it. More development of the payload and drill system. You see 2 videos on the right. This is a 2 times sped up video of the processing of the crucible as it moves around after the drill has filled it. Here's the drill. Here's the brush that knocks it into, in this case, a 3D printed crucible. So this is 2 times sped up, testing all of our states, measuring stations, putting on a cap, taking off a cap. And up top, you can see us testing how the material comes off into these 3D printed crucibles and holders. What you're finding is, you see we're losing a lot of material over here. This design needs to be improved upon, and we since have improved on it. But this is, again, why we're doing this activity. It makes it very much, makes us much smarter with what we're doing. Okay, so the rover that you saw the CAD image of, this is us starting to build it. We're not building a flight rover. So for example, the radiator system, which is what that top deck is trying to represent, is just aluminum. There's no point to test our ability to radiate off heat in an Earth environment, but we tried to make it physically representative. The wheels and the control system for steering and the suspension system is all relevant, although we had to robust some of the design up to work in 1G. Remember, we've got 1.6G on the moon. But to build the 1.6G item and then test on Earth may not give you relevant results, may even cause problems. Heat spreaders, where all the electronics are going and so forth to dump the heat, building up our battery banks. Now revolving a little bit further, very pretty suspension drive system. We built 5 of these, 4 of them for the rover and then 1 for testing, including the driver boards. These are the 1G wheels, which would look a little different, and we've already evolved them since this point, but again, this is the 1-year activity. And starting to build the system together, the chassis bones on each side here, you can see that oven system. Remember the video that was showing materials going back and forth? That's the very device in there as a test unit. Here's a commercial drill from a company called Honeybee that built a engineering test unit for us. They have lots and lots of experience out in different analog environments here on Earth, and so we're looking to them to provide that for the mission. And here, if you've been watching the date codes up top, this is August of fiscal 15. The year mark would be in end of September. And this is us driving around the rover at NASA Johnson in Houston, and it gives you a real sense of scale there. Some of the steering possibilities. You see the solar array in that image there? That again is mocked up. We really are running off of battery power, which are really flight-forward designed batteries, but we charge it on an umbilical system before we went out there. It's all umbilical free now, though, in this activity. We use Wi-Fi for the comm system because we don't need to actually use a space-based comm system. We don't need to prove that either. That's all well understood. However, that is the engineering test unit drill that's in there, and inside of there is that oven, is our lava system, which is what sniffs the volatiles that come off of the oven. You see us pushing ourselves on some of these slopes and over obstacles, frankly beyond the requirements in some cases, but we're challenging the design. We're kind of beating this thing up. I remember at one point we were up at the top of this hill, and there was a pretty sheer cliff, and we were looking to do a rotation. And one of the wheels nearly went off the edge. All the lights flashed in my head, and I thought I saw a tunnel. And it ended up working out because one of the things you'll see in a video coming up is we have the ability to redistribute the weight of the rover across its 4 contact points of the wheels, which could be a very important capability to be able to have. So here's a still image showing you some of the piece parts. You can see the mocked up solar array. You'll notice this looks very different. Yeah, question?
Yeah, since you were talking about the difference between 1G and 1/6G, does it make sense to, like, I don't know, attach helium balloons or something to reduce the weight?
Hold that thought.
Okay.
No, we didn't do helium balloons, but we took that same approach, and you'll see that in a second. But this doesn't look like any of the Mars rovers, not even a little bit. I mean, it's tall, and the solar array's in the wrong place, and what you're seeing here is the nature of the environment that we're going in, which is a polar region on the moon. When you think about that, with my whole description, my head being the sun and the moon and its orientation, the Earth and the sun, well, the sun in particular, never gets more than, say, 7 or 8 or 9 degrees above the horizon from a polar region on the moon. So we have these incredibly long shadows, and solar energy, since we're not nuclear or anything else, is going to come in nearly horizontal, a little bit off of horizontal. And so our solar array, looking up to the sky, does nothing. It's nothing but blackness of space up there. And so the solar array has to be positioned. You see it's on a near vertical. It's playing to that reality of where the sun will be over the course of our mission. And then the radiator system, which this would normally be a not so good place to put that, looking up into the sun. But again, because of where we are, it's going to be nothing but black up there. So it's a great place to radiate off excess heat. And then, of course, you've already seen the interesting way in which it moves. That's all capability associated with us being able to navigate some surprises over rocks and so forth. Yeah, I think that's about it. All right, so I talked to you about some of the Mars rovers. Here's even some other rovers to give you a comparison. With my crude PowerPoint capabilities, these are roughly to scale from an image point of view. You can see the actual dimensions there. So even though we look very different than Spirit and Opportunity, you can see all these fold-out arrays and so forth, we just don't look like that, but we're roughly that size. And this is 180 kilograms. We're heavier than that. Nearly double that weight. You could also see some of the speed performance, although we're not trying to do a lunar speed record, ground speed record, but it's based on what we're trying to accomplish. In the case of Lunicod, it was about getting some mileage under its belt. In our case, we can go as fast as 10 centimeters a second while still making that neutron spectrometer measurement. So we can measure on the fly. We don't have to stop and measure. But our run-out speed is something closer to 25 centimeters a second if we're trying to just get to another place. More drilling in the rock yard, and you can see here we actually took one of those crucibles that we had doped with lunar simulant and actually buried it in the soil. That is not going to be at the right temperature. We're in an atmospheric environment and so forth, but we're trying to practice things like actually positioning the rover over an area of interest, the movement they're in, and then drilling and seeing how the process works while acknowledging we're in a couple of environmental ways quite different than what we'll see on the moon. It's all about the learning. And you'll see on the drill, the flute of the drill is very interesting. Neither of these pictures reflect, I think a previous one showed it. So if you go back and watch this, you can see it. The upper part of the drill bit has a flute that looks much more like an auger. So it's a very high pitch, right? This is the part that's actually trying to trap materials. So it has a very low slope pitch, so the material gets stuck in it. The idea is that at the bottom of the drill bit, when you go down there, you're trapping materials in there, but as you keep going further, you want to move the materials up and out through the auger system. So you're trying to pass material up and out. But this is the area where you want to trap it, and then you pull it back up out of the ground. So here's the trapped soil. And then this brush system is wiping out those flutes where the material's trapped. That falls down into the crucible. And then over here is the crucible shown inside the oven, but it would actually be going out through those brushes, going out there to receive the material outside of the oven, and then come back in and do the magic you saw in the video with running it around into the oven, measuring before, measuring after, putting a cap on it, all those different activities. Houston. So this was in the middle of summer, despite how that looks. And these things come up on you pretty quick. You see clouds off in the distance, and then suddenly this is happening to you. This was our lead systems engineer who just came back in his car. He did run out into this. He was a hero along with other guys. But this tent you see here is actually a cooling tent because it's so stinking hot and humid there. And so there's a big air conditioner system in there, and it's so hot, it's so miserable during midday that you have to go in there and just chill, and there's water in there. So this is the tent that right now you see is almost being folded in half by the wind, and the temperature isn't actually a problem here. We got water that's going inside the tent, and you can see water's pooling around their feet. Guys who are out there conducting the tests actually had to make little dams around the rover, and a few guys were hanging on the tent to keep it from lifting. Hero. And then once it cleared, and that was literally 45 minutes later. Look at the sky, beautiful, cloudy but clear sky. And then we took it back, and it was all fine because the guys were a lot of locals there understand how the weather works, but it was pretty impressive to us. So the culmination. Here I am out in August 21st. The culmination of the work was to actually do the mission, right, on Earth. And so what we did was in the top left picture here. This is at Ames Research Center. You may know Jay and some other folks who are actually with a very low cost, mission construct. This doesn't look like what you're used to seeing in the movies, and that's by design. This is just a bunch of PCs networked together. We're doing the overall mission operations role. And then down here is at Kennedy Space Center in Florida. That's actually firing room 4 for anyone who understands all the different firing rooms there. This is a pretty expensive, well-outfitted place that they put this simple setup in. They are in control of the payload that's on the rover. We're driving the rover around. The honeybee drill that I told you about is actually being monitored out of Pasadena. And this is actually taking place in Houston. So yes, the distances are all wrong. If you're on the moon, it's much more challenging, but we're behaving and operating to procedures that are essentially what we would expect to do on the mission. We didn't give ourselves breaks. I mean, we did in between different scenarios, but we really did a real-time scenario there. This is one of my favorite pictures from the whole activity. You'll notice the interesting framing. There's a big hill that at one point I thought we were nearly going to fall off of. So a guy checking his phone. Any idea what is framing that, this image, the black above and below? Those are sunglasses. So what happened is we hadn't fully calibrated the imaging system when we went out there in that bright Houston light. We had whiteout conditions. And so one of the engineers was there, sacrificed his Oakleys, snapped it in half. The camera, lenses the eyes are this far apart. You couldn't just put a pair of glasses on. Snapped them, duct taped them. Part of the drama that you can't see is there was a piece of duct tape here that was holding each one on. And as the heat was going on, we're all at Ames Research Center. I think I'm sitting right over here. And we're watching it, and you could slowly see the tape starting to peel away. Is it going to drop? Is it going to? It ended up working great. Type innovation we won't be able to do on the moon, but it shows the character of the people who are involved. And then finally, another fun picture. Two of our project scientists, Tony Colaprete and Rick Elphick. You can see that Rick is wearing blue-red 3D glasses and getting, striking quite a pose. He's actually looking at the information that's coming off of the camera that looks down at the soil. We have different LED sources designed into it, so we could turn on and off different ones. And by overlaying the data of those and then comparing it, you could actually get an interesting 3D and scientifically relevant information off of that, let you see things through a different light. I think over the course of the testing, we found M&Ms, we found paperclip. I had a guy go and take some water and throw it over here and not tell the team who was operating it to see if they came across it. We didn't end up venturing over there, so we couldn't say we found water. But we found M&Ms and some other things with the official equipment. Driving tools, this is one of my favorites. It's called VERV. And you can see just the level of fidelity that you have represented in the model, but also the terrain. The terrain is very relevant, a good representation of that area in the Rock Yard over there in Houston. And I was just watching the rover driver work with him. It was very intuitive, how you basically pick and place and do your waypoints. And so it's very impressive. We're developing new capabilities there that will be used on other missions as well. Okay, so helium balloons. This was our version of helium balloons. You can see the black strapping here on each side. You'll see it again, but basically on each side, and then going up with some, ties up to the ceiling. This is in a microgravity type test facility. It's called the Argos facility, and we can dial in the gravity that we want. So what you're watching here is traction testing and navigability. There you can see the yellow strap going up in 16G. So this is representative of the moon, although that soil there happens to be just sand. And we're challenging ourselves at different angles to see what the Grouser design looks like for the wheels. And we even played with 2 different lander egresses, 2 different lander designs. This is quite a steep one, not like what you've seen in the video, but some of our potential partners have posed tall landers, which means you have to navigate this. This is also in that facility. You can still see the yellow strapping. And believe it or not, this looks completely rigged, like it's being held back. This is in free rotation right now, but at 16G. And it's the aluminum treads on the aluminum slope here, which is not an engineered slide, if you will, but you're just getting aluminum to aluminum biting. So it's actually, this is not artificial, despite how counterintuitive it is. It looks like it's being held back somehow, but it's not. And then I think there's one final one coming off of a lander deck that's very similar to what we expect from our lander design that we're currently working with. Okay, so this illustrates some of the navigability of the suspension system, and watch what happens right here. Now, that was more of a tuning issue than anything else, so at first you should not be impressed, but it illustrates an important thing. It's the ability to be able to redistribute the weight of the rover onto, say, 3 of the wheels. Why does that matter? Well, for obstacles potentially and stuff, but the really interesting thing, one of the many interesting things about LCROSS, was in those permanently shadowed regions when we impacted, and we knew when we impacted, we could measure it, there was no impact. For those of you who watched when LCROSS went on, it was a big non-event. Where's the light shining out? Where's the big, explosion that should come out of there? Well, on the spectrum of what could have happened on LCROSS, that's one bookend. The other bookend, though, is one where the softest, downiest talc is in those permanently shadowed regions. And so when we went in with the LCROSS impactor, it was a good fraction of a second before there was a thermal signature that was measurable. At 5,600 miles an hour, a fraction of a second, like 3/4 of a second, is very deep. A lot of distance has occurred at that speed. This has spawned a whole bunch of science associated with the nature of those permanently shadowed regions. Because think about it, there's no thermal cycling going on. It's very, very cold. The principal forces at play may be electrostatic. And so there's been premises put out there of, electrostatically stacked atoms, that are just this cush for when you came in. So how do you navigate that with a rover? And so we don't know what that looks like when you're in the sun. You've got well-consolidated soil. Are you going to, as the moment you have this wheel go into the soil, fall to your belly as a rover? not likely. There's likely to be a transition, but we don't know. Nobody knows. And so the ability to have the capability to move around and distribute your weight, maybe pull yourself out of an area that you got stuck in and back away and then redistribute yourself, might be worth every penny that costs. So these are conversations we're having, including the nature of the permanent shadow region. Seeing here thermal vacuum testing going on here of some of the robotic systems, not the whole rover, but some of the key mechanical systems at temperature, at vacuum. Got some still images too. Of course, tribology, the nature of grease and oil and so forth in these environments is very relevant. Preventing off-gassing or dealing with it with the materials that you choose. Here's vibe testing. It doesn't look like much is happening in the video, but if you look very closely, it is vibrating. So this is random vibe in various configurations. This happens to be in the launch configuration. You see the drill is stowed. It's tucked down to the right. And we're just trying to see what happens to the system and even the individual subsystems that you see in some of these other photos at vibe. This is yet another test of the viability of your system. And as is the case in many missions, the harshest environment it'll see is launch. And so, for example, when we were talking about wheel design in 16G, we actually have to design a system for well beyond what we expect to need on the moon just to survive launch. And that's just the nature of things until we start launching off of other planets where it might be an easier go at it. And of course, looking at stereo vision testing, this is a very strange environment that we're in here. Because the sun is so low on the horizon, the shadows are very long. So black, the blackness of a shadow that has no atmospheric, cross-lighting, it's very binary. So you got whites and you got blacks, and you got whites and you got blacks. How do you tell a hole from a shadow? How do you tell a hill from a shadow, from something over there? That very, very difficult to do inexpensively. You could bring a lot of money to bear and start having laser-based this and that and so forth, which maybe we will end up doing. But again, against the premise of doing things cost-effectively, this represents a special engineering challenge. If you listen carefully, you could hear almost some music going on in the bottom right. This is our lander prototype, CAD model top left, and an actual built model on the right. And then this is a video of us doing cold flow testing. So we're actually running water through the thrusters in different pairings. So it's bouncing around the thruster right now. And then we have, just pipe to carry the water away. And so it's allowing us to just play with timing and then a kind of violent ending. And that's where we're firing them all pretty quickly. But again, it's just a novel aluminum riveted structure that we're testing out the avionics at some level, thruster control. So to close, resource prospector overview, we're about the nature and distribution of the water and trying to move the ball, so to speak, down the field a little bit further. This is what you can expect. This is what you have to contend with. And even testing a little bit of that excavation and processing. When we bake off that stuff, we're going to capture some oxygen. We're going to capture some other volatiles. That could be a very early step to what would end up being required if you were a commercial business coming in and looking to drop pallets all over the surface or down in a permanently shadow region, some sort of device is going, it's filling bottles with liters of oxygen, liters of hydrogen, and then NASA and other companies come and buy it by the liter. And you're creating a whole new, economic opportunity, a new business. So this is perfect use, taxpayer bucks. RPIS specs. You could read it yourself, but there's that mission life that I was talking about. All has to do with the lighting. We could make this a much more expensive mission and go somehow nuke or something that could survive the night, but we don't believe we need to do that to answer the fundamental questions. This isn't about engineering elegance. This is about answering the questions. And there's, I think, a certain elegance in that in itself. Our timeline. Phase A formulation, that was really where we're conceiving of the idea. Then this demonstration, RP15, is what I just described to you, all that testing that we did in a single year. Now we are doing the environmental testing in 16. That was the thermal vacuum chamber testing, the slopes facility testing, the vibration testing, and a number of other things that I didn't show here. And so fiscal 17 is what we're in now. Our fiscal year started in October. And so we're targeting having our system requirements review at the end of this fiscal year, which is September of 17, and moving out as a mission. That's what we're currently targeting. You can see current launch date and so forth. So with that, can't wait to go. Thank you.
In such a low temperature, would your wheels get stuck or stick onto the ground? Like, I don't know, what kind of physics would be expected in such a low temperature?
Yeah, this is a fair question, and this is why we're doing all that testing in different forms. We would ideally have a place where we could represent all the lunar conditions, have lunar simulant, have the temperatures correct, have the vacuum conditions correct, and bring the whole rover in there. That's unlikely. That would be a very expensive thing to do in a very big thermal vacuum chamber. We could maybe do it, but it's a challenge. So what we're trying to do is some of what you've seen here, which is take pieces of it and see how that works. If through our risk management process we determine that it's sketchy enough where these conditions and those conditions, if they combine together, we might have a really bad day when we go to roll off of that lander, we may be forced to do more extensive testing. But we'll see. We're in the middle of evaluating that.
So how again do you redistribute the weight around the rover?
It's all about the mechanical positioning of the suspension system. So you can lower, say, if these are my four wheels, you could lower back corner and just kind of sit back, and that allows you to pull this one out, and maybe you can navigate back under that awkward pose and then reposition yourself and recenter. There's even a strange possibility that I would not call this a designed-in feature, but you could, with such potential articulation, take the wheels and actually move them into an orthogonal orientation where they're not rotating. And depending on what the locomotion looks like, and I'm just imagining here, you could potentially have some form of walking out of it if the traction properties are successful. That's not, like I said, a designed-in feature. But if we find ourselves in a position where, this is really a bad day, then you have the possibility of exploring options.
Is that redistribution done manually or automatically?
Yeah, so that would be done manually on the ground. There's a sliding scale of autonomy, a fully autonomous system, which this is not, and then a fully teleoperated system, which this is not. We give waypoints for our navigation, which means there's some self-guidance, if you will, along the way, auto-generation. But this is closer to a teleop type approach than something fully autonomous. And when you think about it, Mars has it's very different in many, many ways, but one of them is just transport time, communications transport time, that the moon has pretty tight, pretty short transport time. So it allows us to do things with the benefit of humans in the loop that are not really feasible. You have to script everything for the Mars missions just because of speed of light. And so we're trying to play to that because, again, elegance isn't what we're after here. We're just trying to answer the questions. And if the best way to do a short 6 to 14-day mission is with a bunch of people getting tired, but we can all survive doing that 24/7 with shifting and so forth, then we should do that. And that's what we're doing.
Yeah, so I noticed that some of the wheels you had in the demos looked more like gears. It seemed that they would get sort of really good traction, and these look like they're kind of shallow treads that don't look like they would work very well in some of the sandy environments. So what's with the...
Yeah, so the ones that you saw in the pretty video, and I think the one here, are chevron shaped, right? And they were an initial stab at what might work in an environment, and we found that it worked pretty poorly in sand. You even saw it gunking up and so forth. The testing that we were doing on the slope in the microgravity facility, frankly, just had angle iron on it, and it was looking at things like the depth of the grouser and the spacing of the grouser to just try to get some sort of heuristic sense of what's going on. But that's really as far as it would go because there's so much about that testing that isn't relevant, like it isn't lunar simulant at the correct dryness and in a microgravity environment, so we still have much testing to do. So I accept that, yes.
So is there any chance that the data collected by this mission could be used for searching for traces of life or past life, perhaps some sort of extremophiles in this region?
So I'm always impressed. This happened on LCROSS too, where you set out to do these 5 things, and that's what you design the instruments for, to do these 5 things. And then someone comes along and says, you know, if I take half of that and correlate it with this, I could actually pull out this other information. So we're not attempting to do what you're describing. It's all about volatiles. But if we can measure carbon compounds and some other things, I don't know what might end up being possible. But it is not our intention. It's really about resources. It's more of an exploration mission as opposed to a scientific mission, even though we're using science to answer some exploration questions. It is, however, we think, the learning from this is extensible to other places, asteroids, to Mars, and so forth. Not the specific conditions. There's no atmosphere here, and you know, so much about it is different. But the methods of getting to the ore, processing the ore, might have great extensibility to other capabilities. In the case of asteroids, the moon might be actually a very good analog. No atmosphere there, reduced gravity. Yeah, it might be a very good example. So we think this has extensibility, even if you don't care about the moon at all. I think we'll be maturing the sort of the TRL, the technology readiness level of a bunch of technology that will benefit going forward.
Did you try to drill inside caves on Earth to see how places that have never seen light of day correlate to places on the surface, so you know what to expect on those places on the moon?
The correlation of Earth cave areas, I think, would be a little bit unclear with respect to the moon. What we were attempting to do when you saw those canisters, the large canisters by, say, 1 meter tall, was recreate what we believe is the case on the moon with lunar simulant, and then we engineered the doping levels so that we could confirm if we could see it, and even the compaction level. And we've even played with cases where we doped it with certain, you know, rock counts and sizes and so forth. So I don't think we need to go to a natural terrestrial cave area to attempt to mimic what we think we'll see on the moon. We actually are able to create it. Now, the open question is, do we actually understand what we're going to find there? And so trying variations on a theme is hugely important, because when we discover that, guess what, we didn't actually know it the way we thought we did. Does the drill break? Does the drill get stuck? Does it get kicked with a rock? Does it get jammed and I don't have spare fluted bits in my back pocket as a rover? Game over. Do you need to have a way to pop off that drill so that you can at least still scan? These are all things we have to be very deliberate with. But I think we have that handled.
So the results that you might find drilling, are those typically made publicly available in some sense?
Yes. Yeah, that's one of the really great things, I think, about NASA, frankly. Yeah. And that is, while it's a U.S. endeavor, it's partnered in some cases with internationals, and so there's multiple players in there. In the end, we make this stuff available to mankind, right? And so I think that's for the overall good, but the other thing it brings from a more selfish point of view is you get more minds on it, right? Mm-hmm. You get a bunch of different people thinking in different ways on the problem. We don't have a corner on all the smarts out there. So bringing the whole community to bear on data and how you look at the analytics of it, I think is very powerful.
Yeah, you guys are probably focused on the current mission, but I'm curious to know, based on the outcomes of this and the findings, say you do find water in a good enough distribution that it might be worth following up on. What type of missions in the next 10 to 20 years might we see that we could be looking forward to?
Yeah, so under the presumption that we have at least semi-favorable results, meaning we find that the water or maybe other interesting things are available and accessible from an engineering point of view, which I suspect will be the case. We're very water-centric, but it doesn't just have to be about the water.
Helium-3 maybe?
Yeah, so I think what the next missions will look like, and I'm approached all the time by the commercial world, saying that they would do a small-scale excavation activity in from a water point of view, in a juicy area, in an area where it's relatively easy, whatever that means, to get at it based on the RP data. And then I think that sort of creates a pathway to bigger and bigger scales. You could actually envision mobile systems eventually, but you're going to start probably with something that looks a little bit more like a pallet that's placed specifically in a very desirable area. And I think the government and the commercial side will be working together on this. Because while we answer this question, and maybe that now opens up an opportunity for the commercial world to go exploit and make profitable enterprise out of that, the large-scale possibilities going as a next step might be something that's more suitable for government-level risk-taking and dollar amounts, and then that will feed the next. So I see this kind of inchworming thing going up towards really a holistic in-situ resource utilization capability.
Super exciting.
Could your sample be influenced or polluted by asteroids or comets that fly through Moon? And how did you differentiate those?
So I'm not going to be able to answer how you differentiate cometary stuff or asteroidal stuff from other things, but absolutely there's lots of impact gardening going on. I love that term. I did not make that up. Which is because there's no atmosphere on the moon, or at least a very, very tenuous one, that is not protecting the surface like we do on Earth. The surface is riddled with impregnation of materials that have been brought there over a few billion years. It's even postulated that some of the big water finds in some of these permanently shadowed craters may well be the leftovers of asteroids or comets depositing on the moon, since the moon's formation likely didn't allow water that was found at that time to somehow survive. So it's probably all deposition. So now there's yet another marketing opportunity, right? Buying moon water. How much do you think this would cost in lunar water, right? I think there's just untold possibilities here. Even on the commercial side, we're hearing, I speak a lot to the Google Lunar X Prize competitors. I went to the annual meeting last year, and there's all sorts of rich ideas on what to do very explicitly with the material, but also almost symbolically. Bringing things from Earth there and so forth. So there's lots of exploitable possibility here.
So you said the mission is during the lunar day, but wouldn't driving down to the craters make the environment pretty similar to the lunar night, temperature-wise?
Will be from a temperature point of view, but the idea is we can get back out. So we have batteries, and the sizing of the batteries and the sizing of the whole power system are very much driven by that point. So can we go in there and spend, say, 5-6 hours in zero power positive conditions, just using the batteries, and actually operate a drill, bring it up? In the video, unfortunately it cut off, but in the video, we, for example, don't do processing down there. We don't cook it. That's an energy pig. So we get the material and we get out of there. We get back out in the sun, turn our back on the sun, get power positive, and then start cooking the system. So it is similar from a temperature point of view, but we still have calm back to Earth, because even though you're in this permanently shadowed region, we're designing the system to always be able to see Earth, to be able to send our signal there, and to be able to navigate out, because I pointed out we're a little more like a teleop than we are like a fully autonomous system. So yeah, that's designed in, that's intended. It does put a challenge on our mechanical systems design and power systems design because it's very cold.
So about that, about having the rover always need to go from the dark place back to light to recharge and back, have you considered having 2 or 3 rovers, one to just keep recharging the other one in the dark? And it could also communicate with that one, so it doesn't actually have to be facing Earth then.
There's even ideas out there of umbilicals that go to something that's up on the surface, that's enjoying sun all the time. Those are all completely viable ideas, and they may fit more into the paradigm of what you would do in a production sense, right? If it turns out, say, that the water or the accessible water is all down in that 70-degree Kelvin area, so it's tough. Well, yeah, the rim of that crater is likely going to be loaded with all sorts of power generation capability. And at least you'd be able to go up there and sit and park and charge, and you'd have a whole arsenal of these things going down. That's all possible. In our case, though, remember our paradigm. We're trying to just answer the questions, and if we think we can answer those questions about the nature of things in a simpler way that keeps our complexity in check, keeps therefore our likelihoods of failure in check, that's what we're going to peg.
I take it you've heard of the man Bill Stone and the Shackleton Energy Company at all. What are your thoughts on that as a future venture? And I mean, is this like the next oil economy of the space age, the solar system age?
I think all of that is possible. I won't talk about any particular company, but I have spoken with them. At the most recent conference I went to, despite water being very interesting, I had 2 different presenters from 2 different companies who I didn't speak with directly at all cite RP as an important mission because it's answering questions so that they can do very clever things such as actually scooping up the soil there, putting it into this magical hopper, and out come crucibles filling with copper, crucibles filling with iron, crucibles filling with aluminum and so forth, and then you turn that into feedstock for 3D printing.
Yeah, it seems like interesting public-private partnership opportunities.
Oh, absolutely. And the government would benefit from having that capability up there. It could be a profitable enterprise, so the commercial side does. This is a win-win-win, absolutely. And I think it starts with a mission like this. All right, thank you.